Hello, my name is Sterling Summers from Carnegie Mellon University, and this is a pre-recorded presentation for the 2020 International Conference on Cognitive Modeling. I present this work on behalf of my colleagues Alessandro Ultramari from Bosch Research and Christian Libier, my PI, also from CMU. In this work, we're testing the effectiveness of embedding a personal assistant in a cognitive architecture. In the big picture, we are trying to create a personal assistant that would make the same kinds of decisions you would make and carries the results of those decisions in the digital world. A lot of our everyday lives are recorded, for better or for worse, generating a lot of data about us. While learning from this data is intuitively a machine learning task, we advocate for a hybrid approach that uses structured knowledge and machine learning in combination. Because we want our personal assistant to act on your behalf, we want to avoid using any form of aggregate data. Sometimes the choices you make simply aren't the choices of the average person. Finally, because we live in a social world, we often make decisions in a social context, requiring negotiation between other people. But when we make social decisions, we often do so by omitting certain information. So if asked to come to a party with Jane and John, I wouldn't normally tell you that I hate John. I would simply decline the invitation. We expect the same from our cognitive twin. So we are very much in the prototype stage, and we have picked a task that we think we can grow into in the foreseeable future, dinner party planning. If you think about all the requirements and knowledge that go into dinner party planning, you can see that there's quite a lot of room for us to do machine learning and structured knowledge. So, for example, you need to understand that dinners take place at a place where everyone that wants to attend can go, where food can be cooked and it can be served. It has to occur at a time where everyone can attend, and that is during the time that we call dinner. You have to provide food, and that food has to probably be something that you can cook. You have to be sensitive to people's dietary restrictions. And finally, of course, you need people, right? You're not running a fight club. You don't want enemies. You want to try and maximize your friendships, or at least make sure that everyone has a positive connection between everyone else. And you want to capture similar social groups, right? So if you don't want to invite people from your curling club, for example, and people from your motorcycle gang to your dinner, right? That you want people that can plausibly get along. In order to make a model like this, we need a lot of human data. But that's a little tricky at the moment. So there's increasing concerns globally about personal data being shared. And so getting your hands on a database like that is difficult. You can develop your own data by getting a consent ahead of time, but that's both costly in time and money. And so what we decided to do is simply simulate for now. We create data by recording the activities of simulated agents going about their daily lives. Since our test case is inviting attendees to a dinner party, I will gloss over many of the details of the simulation just to provide more information specifically about the social interactions. Social links, or relationships in the simulation, are represented as incoming and outgoing links between all agents in the simulation. Negative value links represent negative feelings, and positive links represent positive feelings, with friends designated as any links above 0.5. At simulation setup, links are chosen from a distribution that is biased for positive connections. Social activities are the source of dynamics in the simulation. It allows agents to interact with one another, resulting in possible change in relationships. Once at a social activity, all agents in attendance interact with one another, and the interaction updates the social link. At this point, we use a bit of our imagination to pretend that people provide ratings of their social interactions. This rating is what is recorded and entered into the model. But these ratings are used to update the outgoing social link. In an update from our previous work, we introduce a parameter alpha to modulate the rate of change in the links. The score is randomly selected from a truncated normal distribution with a standard deviation of sigma, and the influence that score has on the update is modulated by the parameter alpha. Later in the talk, I will discuss how we modify both alpha and sigma to set up change with alpha and noise with sigma conditions in the environment. Let's move on to talk about the models. Models are developed in ACT UP, a toolkit for implementing act are like memory models. The chunks in the agent's memory consist simply of the agent they interacted with, as well as the rating provided by the simulation. So the agents are in no way aware of the ground truth of the links. Each chunk stored in memory has an associated base level activation, the equations in Nectar that are responsible for predicting recency and frequency effects. In order to make a decision, we use blending, which uses a memory retrieval process that produces a consensus estimate, in this case, of the ratings between two agents. This process is going to be affected by activation so that older interactions are going to be less salient in the present decision. There are two versions of the model that we used in our previous work, a central version which simply selects the best guests directly connected to the host, and a distributed version, which evaluates potential attendees by evaluating them against the guests already in attendance. Note that this is an example of twin-to-twin communication, where although the twins are communicating information, the humans only ever see the result, i.e. the guest list. Let's move on to talk about experiments and analysis. To provide a quick overview of our analyses, so the task that we are performing with our model is to select attendees for the dinner party. The evaluation is twofold, so we measure the percent of attendees who are friends with the hosts, and we measure the average connection between all guests at the party. In our experiments, we modify the data quality, so we modify how sparse the data is, and we modify how noisy the data is, and we also modify the rate of change in the simulation. So we want to know how well the model deals with low or high rates of change. To affect the rate of change, we modify the alpha, as alluded to in previous slides, and to modify noise, we modify the sigma. The sigma represents the standard deviation of the ratings, and is set to either 0.25 for a low noise condition or 0.75 for a high noise condition, and they're illustrated on the graphs to the right. Note that a high sigma also affects the rate of change because you're dealing with larger possible numbers in either direction. By making these modifications, we end up with four conditions: a low change, low noise condition, a low change, high noise condition, and a high change, low noise condition, and a high change, high noise condition. We have some fairly straightforward measures to measure what is happening in the simulation. Each of these plots represent what happens over 2 years of simulation. The blue and red lines measure the positive connections and friends in the different conditions. Notice that the lines are generally level except in the high change condition, where there's a decent amount of positive connections lost. While this may look like the social networks are static, if we measure the change itself from day 0, we see that other than low change conditions, there's a fair amount of change, suggesting that some links are becoming negative while others are becoming positive. Finally, in box C, we are evaluating each of the parties in the simulation from day 1, measuring the percent of friends with the host in brown and the average connections between guests in black. There is no discernible change in the simulation score here. The real takeaway is that the simulation scores roughly 75% friends with the host and roughly a score of 0.4 for connections. In our first experiment, we modify how much data to use by reaching n weeks back from the end of the simulation. The graphs on the right represent how well the two models did in our two measures. We are looking essentially for two properties. One, the overall average, which in most cases is better than the simulation, and two, the steadiness. From left to right, we are adding data further back in history. Because the environment, at least in the high conditions, is dynamic, that data can become outdated, especially after 2 years of simulation. A steady result suggests that the base level decay of memories in the model is providing an advantage by effectively discounting older data. We don't notice an artifact in the low change conditions, the blue and the red lines. In those, we see an increase in performance with including older data. The relative low starting score in those conditions, combined with the increase in performance with more data, suggests that the base level decay is actually a hindrance. It might be the case that the base level decay is overcompensating in a low change environment. As a measure of sparsity, we see that the model can exhibit strong performance in both measures with very little data, as little as a few weeks. There are other insights to be gained, but I'll have to refer you to the paper for those. In experiment 2, we explored data sparsity in a different way. We probabilistically remove data from our data set, including as little as 1% of the data. This might actually be a more realistic way to simulate sparsity, as we can't expect people to always provide ratings or the data always to be available. The data loss as compared to the week's data is less advantaged here because there is no trend to capture. The data is just simply lost. But still, we see the model is quite robust, especially after we include 25% of the data. But even with as little as 10% of the data, the model still outperforms the simulation, even in the high change conditions. Again, there is more insight to be gained here, but in the interest of time, I'll refer you to the paper. Our final test is to modify the decay rate parameter in the model itself. We modify that parameter from a generally accepted value of 0.5, which we used in all the previous analyses, and increase the decay rate gradually to 0.9. Generally, both the central and distributed model maintain steady performance in the high change condition. In the low change conditions, however, we see a decrease in performance as we increase the decay rate. This decrease in performance helps push the idea that the base level activation is a hindrance in a relatively static environment. Well, in some regard, this is a concern. The low change conditions may, in fact, in hindsight, be unrealistically low, as the simulation statistics described previously a few slides back show no real evidence of change in the social networks, which in hindsight seems unrealistic after 2 years of simulation. So all in all, I think we're pretty pleased with how the cognitive twin has worked out. The cognitive systems seem to benefit, at least in a dynamic environment, with the baseline activity degrading older information and favoring new information, allows the models to sort of adapt towards the change in the social networks. In hindsight, we would like to explore better a range of values for alpha and sigma. In the low change condition especially, we suspect that those values were a little bit too low, and so we would like to see the performance of the model in a broader range of values for both alpha and sigma. Another way we are at least planning to work forward is to change the veridicality of the simulation and maybe add more details in and learn more stuff with the digital twin in the dinner case. So we would like to, for example, modify how the social circles are developed. So you might have a different social circle with people at your work or with your family, and not just sort of random interactions. And while we have details for food, we would like to be able to use those details in the digital twin itself. So there's still a lot of ways in which we can improve the simulation and improve the digital twin, even within our little party planning scenario. Thank you so much for listening. I hope you enjoyed the talk and you bring any questions on question day. Thank you.